Dear students, in this class we are going to study the Wien bridge oscillator using a op amp. Because we have not gone through the op amp chapter, I will briefly tell you what is an op amp. Then let us see what a Wien bridge oscillator is. After that, after this class, let us go back to the op amp or operational amplifier chapter. Okay. So operational amplifier, it is known as operational amplifier. Operational amplifier. Amplifier, as you know, something that amplifies. It amplifies the device. Operational, it does operations. What operations? Does mathematical operations. Mathematical operations. What are mathematical operations? You might know that keeping it as it is, unity. Let us begin with the simplest. It does the unity operation. That means that input is equal to output. I will write it in the short form. Okay. Input is equal to output, unity or inverse output is equal to minus input, negative of the input, and then it also does addition. So output is equal to input 1 plus input 2. Subtraction, similarly multiplication, you can do integration, differentiation, like this. These are the operations and many more, of course. I will just put 3 dots. Many more operations can be done using a operational amplifier. Okay, so that is why it is called operational amplifier. It does mathematical operations. These. Look at the image here. More important is to understand this image. Okay, so here are the two inputs. You can give two inputs to an operational amplifier, just say op amp. It requires a battery with the plus, usually plus and minus 5 volts or plus or minus 12 volt. You need plus here at the top and bottom minus. I will explain it to you with a IC later, putting an IC in a circuit. Then the output, you get the output here. So why this? The interesting thing is the minus sign and plus sign here. What does that mean is, suppose you feed the input to the inverting, this is called inverting terminal. Okay, that is because if you feed it to this terminal here, then the output will be negative of the input. So if you feed a, let us say, sine wave like this to a negative, then output will be amplified but having opposite phase. So if you feed input to the positive, then the output will be same phase. So here out of phase, here in phase. That's all. Okay. So whatever you feed, its opposite sign will come out at the output. So if you feed a DC voltage of say -2 volts, the output will be amplified. So note the size of these waveforms. That is why I made them bigger. So it is amplified. Along with that, some operation is done, and by suitable combination of these inputs and by making use of capacitors, inductors, resistors, the output can be designed as per your requirement. Okay. So that is basic about operational amplifiers. So here is circuit, of a oscillator making use of op amp. So oscillator we have already studied. So we want to create a circuit that gives us an output which is oscillating. So you need a plus V minus V essential for an op amp, and then you have a output, and then there is a resistor here, RF, and then output, and then you need another capacitor and a resistor circuit towards the positive input, positive non-inverting input scientifically, and then here you have a resistor and a capacitor, and then they are connected to the ground. Here there is a resistor and that is connected to the ground, and this is R1 and this is RC. Alright, so this is, and here what is actually used is tungsten lamp. I will explain you that. Okay, so this is the Wien bridge oscillator, WIEN, Wien bridge. So it is an oscillator that is used to produce frequencies between 5 Hz to 1 MHz. So that is the range of frequencies you can generate using a Wien bridge oscillator. This uses both the inputs as a combination, and then these frequencies is given by 1 by 2 by RC. So by changing the resistor, capacitor in the circuit, you can change the output signal, frequency of the output signal. By varying this, what is known as feedback, you can also vary the amplitude of the output signal. and this bit consisting of the resistor and capacitor is known as lead lag network. Lead lag network. So that is basically to satisfy Barkhausen criterion. Okay. So this is the circuit that is necessary to satisfy the Barkhausen criterion. That is A beta is equal to 1. Okay. Here you can also look into the book, photograph of the book I have sent you. Here beta is set to be 1 by 3. Okay, beta is set to be 1 by 3 and A is set to be 3. Okay, so this is the feedback, this is what? This is the amplification. You can set the amplification of an operation amplifier. We will know it when you do the circuits just by varying the resistor outside. Okay. So by doing that, what you get is you get a oscillatory output without any input. So so the negative feedback is on the top. You might see there the minus side of the op amp is connected through a feedback resistor and another resistor R1, and therefore the amplification is actually given by 1 plus RF by R1. Okay, so this part, the top part, tells you the amplification factor of the op amp. So to have Barkhausen criteria satisfied, to satisfy Barkhausen criterion, A should be equal to 3, and that is 1 plus RF by R1. So RF is equal to 2 times R1. 2. As I told you, you can set the amplification factor. And then the Wien bridge name is basically Wien bridge. Sorry, I always get confused with this. WIEN, Wien bridge is the feedback pad at the bottom that consists of one capacitor and a resistor in series, and one resistor and a capacitor connected to the ground. So RC, this is known as the Wien bridge. Okay, bottom part. The oscillator is called Wien bridge oscillator because the resistors R1, RF, series RC, parallel RC, all of these together form what is known as arms of a Wien bridge. Under stable oscillating condition, the bridge is balanced. So how it works? As it's said in the working, when the power is switched on, you switch on the power, the tungsten switch on, R1 is low, tungsten bulb has low resistance because it is just switched on. Okay, R1 is low, therefore A is equal to 1 plus R by R1 is large. Okay, as I told you before, the signal noise gets amplified. Amplification is high. A is much more than 3. After, so then there happens to be oscillations of large amplitude and A beta is much greater than, or just let us say greater than 1. And oscillations are built up at the resonant frequency. Okay, output increases at f naught. So actually, otherwise, if you just amplify without putting this R and C, then you see the noise amplified. Okay, that is what happens in our auditorium when somebody drags the mic stand. Okay, a you hear a loud noise, loud noise. It's basically made up of many frequencies and it's all amplified. Okay, something like that happens. But here increases at f naught, so only that frequency is amplified. After some time, remember the time after few milliseconds. Okay, it's not a lot of time though. After few milliseconds, bulb reaches its maximum temperature and R1 reaches its maximum value. Okay, and at this condition, A is equal to 1 plus, or you can say R2, R1 is equal to RF, or RF by R1 is equal to 3. And that gives you rise to sustained oscillations. Okay, so that gives rise to sustained oscillation. So initially Barkhausen criteria is not set, but later it is set due to the heating of the filament in the tungsten lamp. Just a brief introduction about the lead lag network. It is, as the name says, lead lag. Okay, so a lead lag network basically consists of series and parallel combination of RC circuit. So it happens that for AC alternating current, capacitor is like a pass. So this is a kind of, one of them is lead and then another one is lag. Lead and lag. So lead part and this is lag part. So if you vary if you vary these two capacitors, I mean if these two capacitors are not equal, then you can make the circuit such a way that input and input leads the output, input leads or leads the output, or input lacks the output or input in phase with output. So this is if C1 and is not equal to C2, R1 not equal to R2. So one of them has to be larger, one of them has to be smaller. Here C1 is equal to C2 is equal to C. That is what we have done in Wien-Bridge oscillator. Then your circuit is not a lead or lag, it is both lead lag. So it leads as well as lags. That means they go in phase. Just like ನೀವು ನಡೆಯುವಾಗ ಇಬ್ರು ಫ್ರೆಂಡ್ಸ್ ನಡೀತಾ ಇದ್ದೀರಿ, ಒಬ್ರು ಬೇಗ ನಡೀತಾರೆ, ಸೊ ದೇ ಆರ್ ಲೀಡಿಂಗ್, ನೀವು ಹಿಂದೆ ಇರ್ತೀರಿ, ನೀವು ಲ್ಯಾಗಿಂಗ್. ಸಪೋಸ್ ನೀವು ಬೇಗ ನಡೆದ್ರೆ ಯು ಆರ್ ಲೀಡಿಂಗ್, ದೇ ಆರ್ ಲ್ಯಾಗಿಂಗ್, ಬಟ್ we don't want both of those here. Here we want lead lag to be the same because we want the same phase, or we want a fixed phase difference. Okay, suppose ನೀವು ಕೋವಿಶೀಲ್ಡ್ ತಗೊಳ್ಳಿಕ್ಕೆ ಹೋಗ್ತಿದ್ದೀರಿ ಅಂದರೆ we need a fixed lead, we need a fixed lag. So those things can be set by changing the two capacitors separately. Okay, so that is the about the lead lag network. It's basically due to the presence of the capacitor we can have this kind of performance by the circuit. So just I will read what is in the book. At very low frequencies, the series capacitor offers high reactance and works like an open circuit to the input voltage, and hence there is no output voltage. At high frequencies, the shunt capacitor offers low reactance and works like a short circuit, hence no output. In between these extremes, so therefore, who will be fed back from the output to the input? Only that frequency which is not sent to the ground by the shunt capacitor. Shunt capacitor means the capacitor connected to the ground, and a frequency which is allowed by the capacitor that is in series. So frequency selection is also done by this. So another important job is done by frequency selection is done by this feedback circuit. At very low frequencies, the phase angle is positive and the circuit acts as a lead network. At high frequencies, the phase angle is negative and it acts as a lag network. At resonant frequency, at high frequencies, okay, output positive and this is lead network. So lead network at low frequencies. Or this is at resonant frequency. So just you should remember, so at resonant frequency, so at high frequency, at low frequency, and at resonant frequency. So at resonant frequency, output is in phase with the input. Phase shift is 0, and the feedback is to the non-inverting terminal, positive terminal. Therefore, the op-amp also not introducing any phase shift. You remember in transistor introduced a phase shift of 180 degree. Therefore, we had to compensate that using 3 sets of RC circuits. Here that is not the case. So with that we complete this unit. Okay, we complete this unit. I will ask you questions until this class in the test, in the internal exam, most probably conducted on Saturday. Good luck.